let us revise what we started to do yesterday. So, what is an isometry? An isometry is a mapping from R3 to R3, which is keeping the distance. And this is the formula which states this. So the distance of the images is equal to the distance of the starting point. Okay? Then, with some simple reasonings, which I sketched yesterday, and I advise you strongly to revise by yourself, even before I send you the written notes, it is rather easy to prove that why this is easy. Because we have Cartesian geometry. So we can represent this mapping using the methods of Cartesian geometry. You have the coordinates of the starting point and the coordinates of its image, and you have the theory of linear applications between vector spaces. So if you try to prove the structure of an okay, there is a problem in this better if I pronounce it in the correct way. In American and British English, for some strange reasons, they call it, even if this is a Greek word, they call it isometry. Okay, but I said it Greek, Italian way. So I will try to say isometry. We will meet also another word, I will tell you in later. This word is Greek, and it has been written in English exactly as it is written in Greek. And it means a conceptual structure which you are following in doing some intellectual efforts. This is a brutal definition, and we can do it better. Okay, even if Americans and British are calling it and pronouncing it paradigm, because they cannot read this sound, I refuse to read it paradigm. So I will read it paradigm, because this is the Greek word. You cannot change as you like this kind. By the way, my friend Daniel is, after he knew about the etymology of this, pronounces it both ways. Because he's of Indian origin, so he is sensitive to the history of science. Okay, so when you have an isometry, and you want to prove its structure using Euclidean geometry, you may have a lot of troubles, because the demonstrations are complicated. You need complicated triangles, and you need complicated arguments if you want to use only geometry, Euclidean geometry. But you remember in the proof which we have sketched yesterday, we started with Euclidean geometry. We said that an isometry is mapping triangles into triangles, okay? But after this, what we did? We introduced the inner product, okay, between two vectors, and also for the inner product of two vectors, you have two sides of the concept. The purely geometrical one, so the inner product between two vectors is the length of one vector times the length of the other vector times the cosine of the angle, or, you know very well, if you decompose the two vectors into a basis, orthonormal basis, then you can calculate the inner product as the sum of the homonymous components. Okay? So also the inner product has two phases. Cartesian, geometry. When you introduce the angle and the cosine of the angle, you are considering the inner product in its aspect, more geometrical aspect. When you do the same on the other side using Cartesian coordinates, you take the components of the two vectors and you can build with algebraic products and summations the inner product. We exploited these for jumping from one aspect to the other aspect of our story. So in our demonstration, we did easily what can be done easily with Euclidean geometry, and we did easily what can be easily done with Cartesian geometry. Okay? So this is the trick we have used for arriving quickly to the result. Okay, so what we know that every isometry is represented in this way, where Li is the linear part associated to the isometry, and this Li therefore can be represented as a matrix if you have a basis, but this Li is orthogonal. So it verifies this equality, which means that the inverse of Li is equal to its transpose. Okay? So this is the point. Now, if I have a limited body and its motion is the motion as a rigid body, the application key which maps material particles in omega into their actual position keeps the distances, of course, only of the points inside the body. Okay? But the representation theorem holds for this. So, as we said yesterday several times, you can extend this key to the whole space. So you can imagine that your body, rigid body, has glued to it a whole set, infinite set, a whole space, a whole three-dimensional space of points which are moving rigidly with it. Okay? And this is the a trick which has been, a mathematical trick, which has been used by many engineers for building machines. The invention, the invention of the constraint which keeps the door rotating around its axis. Okay, the axis around which the door is turning is not made of points of the door, because physically this would block the door. However, you imagine there a set of points which are associated to the rigid body door, and you say that this set of points is blocked in space and the door is turning around it. Okay? So, once more, it is not true that mathematics is abstract and not influencing technology. You think in terms of mathematics. What is dangerous is that some practical people believes that the axis of rotation exists. They believe to be able to touch it. It is the materialization of mathematical ideas, which is very dangerous. Mathematical ideas live in another world. Isometries were studied for millennia, and they were considered one of the most important subjects in technology and mathematics. But only recently, with our strong computing tools and exploiting these formulas, we are systematically using it in the applications. You will see very nice numerical simulations which start based on the use of this formula. Okay, so coming back to our moving body, the position of any particle of the body, if the body is moving with a rigid body motion, can be represented in terms of the position of one comment, which we have called the origin. Capital X0 is the point in the reference configuration, and small x0 is its actual position, plus an orthogonal matrix applied to the displacement vector xp minus x0. Okay? Okay, so the position of every point of a body moving in a rigid motion can be represented if you know these coordinates. One position vector and one orthogonal matrix. And this we will need for making some discussions about space of configurations and finite dimensional space. Okay, so what I want to tell you now, here we have a nice mixture of mathematicians and engineers, and I think it is very good. You should try to discuss. Maybe while forming groups for the final presentation, we should mix engineers and mathematicians in order to have a kind of interaction between these different groups. Let us think a little bit. Anisometry is an abstract concept. It is a mapping between R3 into R3, which is preserving distance. Then you can consider the rigid body motion. The placement, the function key representing the placement of a rigid body motion is a particular isometry. So you can use the general theorem for every isometry to that particular case. Okay? Yesterday we have spoken about change of observers. The mapping which takes one observer, the coordinates measured by one observer, and transforms them into the coordinates measured by another observer is another particular case of isometry if you accept the postulates of Galilean mechanics. Okay? So, what should do a mathematician? He should study in general isometries, and then he should apply in particular cases the general concept introduced and the general results proven for this general concept. What I want to say, you will not prove another time for a rigid body motion this formula. You recognize it is a particular isometry and you use the general theory. You want to talk about change of observer, you don't prove another time the theory. You recognize that the change of observer is an isometry and you use the general theory. My dear friends, this is the big problem of modern engineering schools. They study in one class rigid body and they prove the theory. They study in another class change of observer and they prove another time the same theorem. And very often, if you ask to this student, there are similarities, he says, no. Placement, rigid placement is solid, change of observer is another thing. So they cannot make the abstraction which led us to understand there is a common feature between rigid body motion and change of observer. The very big problem of the modern engineering school is related to the fact that the effort of abstraction is not anymore imposed to the student. But also mathematicians are becoming strange because they refuse to make their hands dirty talking about applications. So if you tell to a mathematician isometry, they are happy. You talk about rigid body motions, this is physics. I refuse to even talk about this. Okay? And this is very bad. So, when I proposed this course to the Department of Mathematics here, I wanted to try to invent a course in which these 2 points of view could come back to Archimedes. You know, Archimedes has proven wonderful theorems and has built wonderful devices. The same person could do all this. And this spirit must be recovered. Okay? So otherwise our civilization risks to be lost. Okay? So please try to follow this continuous change of point of view. Because you must learn to use both of them. Once you have written this equation, you forget everything about physics. You make calculations. So now we start doing some calculations for finding a beautiful formula representing the velocity of a point in a rigid body motion in terms of the velocity of the origin and something we will try to discuss about Q and Q dot. We will try to make clear what angular velocity is. Okay? In the literature, they talk about so-called M&MoCS theorem. Okay, M&MoCS was an Italian scientist in the Renaissance, Middle Age Renaissance. Okay, but I strongly suspect that, like very many scientists of that epoch, he had a very good Greek book in his hands. Okay. By the way, if you go in Persia, they talk about Greek mathematics translated in Persian. There are many books, Greek books translated in Arab. There are many Greek books translated in Latin. Many books were reconstructed, many Greek texts were reconstructed comparing the translations in Persian, Arab, and Latin. You see? So it is difficult to say who invented this equation, these formulas, but we are using modern concepts, in particular the concept of derivative. Okay, so we go ahead and we calculate the derivative of this equation here. Okay? This derivative can be easily calculated. I call Vp the derivative of xp. Okay? So this is an equality by definition. x0 as derivative v0. Then you must make the derivative of this. Okay, I hope you are not worried, but I tell you how easy is what we are doing. If you have a matrix Q and you have a vector V, okay, and both of them are depending on time, and you want to calculate the derivative of this. By the way, I'm giving as granted something. Maybe I was wrong. What is the derivative of a vector function? The derivative of a vector function, you represent the vector in terms of components. The derivative of the vector function is the vector having component-wise the derivatives of homogeneous components. Okay? So if you have a vector V having V1, V2, V3 components, V dot is simply this. So the derivative of V is V dot 1, V dot 2, V dot 3 components. Similarly, the derivative of a matrix function. So you take the derivatives of all components. Of course, this is a Cartesian definition. Okay? We can give also a direct definition producing the same result. If you have a vector V of t, and you have V of t plus delta t. Okay, what can you do? You take V t plus delta t minus Vt. You can do this. Why? Because vectors, you can make the subtraction of one vector from the other. Then you can divide this with delta t. Delta t is a real number, so you can multiply one vector for 1 divided delta t, and then you can calculate the limit of this when delta t tends to 0, and this is by definition v dot of t. Okay? Now what it means, this limit? This is also rather easy. If you have a vector function w of t, the limit for t tending to t0 of this is equal to w0 by definition if limit for t which tends to t0 of what? Wt minus w0 norm is equal to 1. Okay, so I have reduced the definition of the limit of a vector function to the definition of the limit of a real number function. Okay? So, the length of this difference becomes smaller and smaller. And the length is a real number. Okay? So you know for sure what is this, what means this formula, and I tell you that the limit of a vector function is, depending on time or a real parameter, is a given vector W0 if and only if by definition you have this equality. So I've given to you the meaning of this limit. Okay? So what I'm telling you is that either you introduce this definition or you introduce this definition, you get always the same result. Okay? If you have represented the vector in a given basis. You know why it is very good if you understand this point. Why I prefer this definition? It is coordinate independent. One, not an engineer, a mathematician, could start suspecting that the definition of derivatives depends on the coordinate. If I use this definition, a mathematician could be very suspicious. He could say, okay, I change reference, I change basis for my vectors, and the derivative is another mathematical object, is another vector. This is a possible suspicion. How do we avoid this suspicion? Proving that this definition, which is coordinate independent, produces as a theorem this definition. Okay? So we can conclude that the first definition which we have given is coordinate free, independent of the reference, the basis we have introduced. Okay? So look, I am making an effort to tell you everything in the smallest details possible. Okay, I cannot give you the definition of a limit of a real function. Okay? I can give it, but you know, not here. Okay, so by the way, the poor Galileo needed several hundred pages for describing in words this. Now we can do it quickly with some powerful mathematical tools. Of course, if you want to write all the definitions behind this deduction, you need 100 pages. So there is a kind of conservation of pain. However, if you learn what is a derivative, you will not use only for this case. You will use wherever you need the concept. This is the reason for which it is very good for engineers to study calculus without talking about applications. Because in this way you are ready to apply the abstract concept in different applications. If you learn what is a derivative in a particular application, you think that this is a more particular case than it actually is. At the beginning of my career, I was teaching to economists. Poor economists are in a worse situation than engineers. They repeat the definition of derivative for every function they need. They talk about the rate of change of costs, the rate of change of gain, the rate of change of offer. I mean, they repeat always the same reasoning. Simply because they do not want to study in an abstract way the concept of derivative. Okay, the difference is that engineering became a scientific discipline together with a mathematical analysis, and at the beginning engineers and mathematicians and physicists were studying all together. So there is a common language between these three groups. Okay, now, what is the derivative of this product? Leibniz rule holds. So, W dot is equal Q dot times V, capital V, plus Q times V dot. Okay. Do it as an exercise. Q is a matrix. V is a vector. You can make the definition for V as the first component of V is what? The first row of Q times capital V. If you are patient, you prove that this rule holds also for the product between one matrix and a vector. Okay? Actually, it holds also if Q is a matrix and V is another matrix. And you are multiplying row times column, the two matrices. Okay? Now, we have a very nice situation in applying this general result in our particular case. Which is this very nice situation? XP and X0, capital XP and capital X0, are time independent. So the time derivative of XP and X0 is 0. So the velocity has this form. Okay? Now, both mathematicians and engineers are puzzled by Lagrangian and Eulerian description of the motion. So I want to use this formula and go ahead in discussing this formula because I want to make clear that there are two different ways to describe the motion of a body. So what is doing this formula? This is a typical Lagrangian or material or referential formula. You know the coordinate of your material point P in the reference configuration. You know the coordinate x0 of the origin in your reference configuration. You know these two quantities, and you can place every point in the Eulerian or spatial or actual description. So, you have your body. You painted here a black point, and you follow the black point. So you have always the same material point. When you have fixed capital XP, you run on the fixed material point. So you are considering a Lagrangian or referential description. We call it Lagrangian because it was Lagrange who invented it. Maybe was the first one explicitly using it. Okay. On the other hand, you could be in one position. So imagine to have chosen one position. So you place yourself somewhere, and in time, the body, in a distance t1, a distance t2, the body is crossing the point x. Okay? So in small x, you have different material points in different instants. Okay? So what you may be willing to do, you may be willing to say, given an instant, there is a material particle in that position. Which is the velocity of the material particle which is there? This material particle changes in time. Different material particles occupy x in different instants. Okay? Could be very beautiful if before dying I would manage to make this lecture with a movie from SolidWorks or from working model. We could see the computer showing you the body moving and all the arrows. I did it one time, then the software, they changed the operating system and I could not recover the software for the new operating system anymore. Okay, so you see all the arrows of the body, of the position of the body, and you follow, either you follow a material particle in its trajectory, or you stay in one point and you see how the material particles are passing. Okay, let us think a little bit. Where is it important to study Lagrangian, to use Lagrangian point of view? If you have a solid body which is moving in the space. When it is useful, more useful, to assume an Eulerian spatial point of view, imagine you have a channel, you are pumping here water, you are pumping out water there, and you want to study the flow of your fluid inside this pipe. So, Eulerian point of view is very useful in fluid mechanics. Lagrangian point of view is very useful in solid mechanics. However, think about this. What it means, the velocity of a moving body, is always the derivative with respect to time of the Lagrangian position function. You fix you remember, V of P and T, as we have defined yesterday, is equal to the partial derivative with respect to time of key P fixed, time T varying. Okay? You cannot define velocity in any other way. For some mysterious reasons, in many fluid mechanics classes, they manage to talk about velocity without never introducing this key of P and T. This is a mystery. How they want to manage. So, another reason for which I'm losing investing 1 hour and a half and even more of your time in making this derivation is that this is a very simple, for solid, rigid body motion. It's very simple to move from Eulerian to Lagrangian description. And Eulerian and Lagrangian description are both very useful in our discussion. Okay? So, this is a Lagrangian description for placement, and this is a Lagrangian description for velocity. Okay? Okay, let's move another step. I want fixed small x. I want to find the velocity not of the point P, one fixed point P here. I want to find the velocity of the material particle which in a given instant is in small x. So I want to write a formula for rigid velocity in Eulerian description. So what I'm doing? Very simple, because I have linear algebra. I have read books in fluid mechanics who are a nightmare. Okay? So what we do? xp minus x0 is equal to q x capital xp minus x0. I've taken this and I place on the other side. Okay? Then I can multiply everything times q transpose. Q transpose Q is identity. My dear friends, this is the beauty of mathematics. You do operations without thinking. Okay? If you need, you interpret your... This is an algorithm. We applied algorithmic transformation to our equations. Okay? But we have an aim. Why I'm doing these calculations? I want to get rid of these Lagrangian equations. Okay? These Lagrange coordinates. So what I'm doing? Please copy another time the equation. So I am erasing this formula here. And instead of xp minus x0, I place q transpose t x p minus x0. So I place now myself in a point x. In that instant t, in this position, you have a material particle. I call it p. Which is the velocity of the material particle which at instant t is placed in x? This is the formula. So now we have a fully Eulerian description of the velocity field. In every time instant, in every point of the space, so in every position, you can tell which is the velocity of the rigid body which is occupying the whole space and moving with a rigid body motion. Okay, and this is the typical Eulerian formula. Okay? Let's move a little bit another step. What is Q dot Q transpose? So we must study now this object. Okay. I could do very complicated geometrical reasonings, but let's go back to algebra. Okay? By the way, look, I am stopping sometimes what I'm telling you, not because I am lazy or I want to lose time. It is well known since the age of the democracy in Athens that nobody can be attentive for more than 10 minutes in a row. If I talk in a continuous flow, he will stop after 9 minutes. He will stop after 10 minutes, 20 seconds. He will stop after 11 minutes. and I will not have a synchronous group following what I'm telling. If I stop in a given moment, then at least I get that who wants to follow me is following me and you are following all together. So I give you the interruptions. Okay? Very well. So the big trick now is to use the algebraic structure, of rotations as represented by linear applications to find a nice structure for this Q dot Q transpose expression. Okay? So what I do? I calculate the derivative of this equality. So we need Leibniz rule another time, and we need Leibniz rule for the multiplication of two matrices. Okay? So what I have that Q dot transposed Q plus Q transposed Q dot is equal to 0. Okay? We want this. Okay? So, as usual here, 50% of times I use the wrong order of transposition. This is equally true. Okay? So, Q dot Q transpose, which is this matrix here, is equal to minus Q dot transpose. Okay? Okay. This is equal to Q dot Q with minus transpose. Transpose here. Okay? Because general rule the transposition is reversing the multiplication order. Okay? So if you have, look, I give you this exercise. Go to the definition of the transposed, which I gave you yesterday, and prove this. Okay? I give you another exercise. Please try to do it. I give you another exercise. If you have a linear mapping, which is represented by a matrix, the transposed linear application is represented by the transposed of the matrix. Okay? So you can prove this also calculating easily the transpose of the matrix. Okay? This is a true basic property in linear algebra. Okay, I write it bigger. So this is equal to minus Q dot Q transpose. Okay? You apply this, you get Q transpose, which is Q, because if you transpose 2 times, So you get it back, okay? And you get Q dot transposed on the other side. So what you have proven? Q dot Q transposed is skew symmetric. It is equal to minus its transpose. Okay, I hope you are familiar with skew symmetric matrices. So, Q dot Q transpose, which by definition we call angular velocity, is a skew symmetric matrix. So what we are telling, and this is the final classical statement of M&MoCS theorem. You have a body which is moving with a rigid motion. You choose one position, x0. You know the velocity of the material particle, which in that instant is in x0. This velocity is v0. This velocity usually, sometimes is called translation velocity. The velocity of every other point in your rigid body motion can be calculated adding to V0 the inner product of WT skew symmetric matrix, not the row times column product of W with X minus X0. So you know the velocity of every material particle if you know the velocity of one material particle and WT. Okay? Now, WT is called angular velocity. Now, look at this formula. Can you talk about the angular velocity of one point? It is totally meaningless to talk about angular velocity of one point. You can talk only about angular velocity of a body. P has been forgotten. Yes, you are right. You are right, I'm not consistent. Either I write it here, or I erase from everywhere. Okay. I wrote P because I wanted to leave a trace of what? The material velocity which finds in X as the velocity V. And I called this material particle with P. Okay? So it was a souvenir, recalling of all the reasoning which I did for reducing that formula. But at the end of our story, this formula is a purely Eulerian formula, and it makes a picture of the velocity field in space, in Eulerian space. Okay? So you can understand why some fluid mechanicians try to talk about velocities without ever speaking about x, capital XP, the placement key, and the position occupied by the material particles. Because they always deal with formulas like this one. Okay? But this formula is totally meaningless if you don't have key behind it. And we needed, for deducing this formula, to replace capital X in terms of small x. Otherwise, it is totally impossible. It is completely meaningless for us. Okay. Now, let us move another small step. I need that you practice a little bit with linear algebra, but you should know. Everybody among you should know this. So I have W, which is a skew-symmetric matrix. This is a possible representation of your number. Okay? This is a skew-symmetric matrix. Now, Gibbs has invented the vector product between two vectors. I'm sure that you have studied vector product. Did you study vector product? Yeah? Did you ask ever yourself why ever we need to introduce vector product? Who had the idea for introducing vector product? Why it is so useful? And most important, why I must use the right hand law, and if I use the left hand law I get another result, and more complicated, why you need a right-handed vector basis for calculating component-wise the vector product, and if you don't use a right-handed vector basis, you get minus the vector you had before. When these things are happening, it is because you are not understanding something. Now, I try to explain you what is really happening. You choose right-handed basis, and you introduce the vector product using right-hand definition. Then you have a skew-symmetric matrix U. You apply it to a vector U. What you get? A vector. Okay? The idea of Gibbs is I am bored with skew-symmetric matrices. So instead of considering omega, W, I can introduce a vector omega. And once this vector product is defined, I want that this equality is true for every u. So, in a sense, you can make this definition of vector product. You can say the vector product is that product such that for every skew-symmetric matrix W, W applied to U is equal to omega vector U for a specific unique omega. So, given right-hand vector product, so if you have defined this, you can say that for every W there exists a unique omega such that for every U this equality holds. Okay? The good news is that you can find this operation. The bad news is that if you have right-handed vectors, you represent it in a way. If you have right-handed bases. And if you have left-handed bases, this vector omega changes. Not so much. It is minus the other one. So in books of physics, when I read this, I became crazy. You find that there are some pseudo-vectors. So what is a pseudo-vector? Define it. No, they write cross product introduces pseudo-vectors. Without a sentence for, they send you a message like that. And you must break your head for understanding it. So in a sense, this is a trick. Angular velocity is a skew-symmetric linear application. If you really want to introduce the angular velocity vector, then you need to introduce the cross product. You must fix right or left hand vector product, and then you will have a vector related to your skew-symmetric matrix. But I'm sure that if you ever have seen this formula before, this is what you have seen, where omega is the angular velocity. Okay? Okay, so we did enough technical considerations for today, and now we start making mathematical physics considerations and modeling considerations, because I want to try to explain you the reason of the title of this course. Okay? So please, one question at the exam, one question in the list of questions for passing this exam will be the deduction of these formulas. It is very important because I check that you know enough linear algebra for going ahead. These equations are very important in the whole mechanics of bodies. We have spoken about Eulerian and Lagrangian description of motion. So there are many concepts behind these calculations. And you cannot do these calculations easily if you have not understood the basic ideas behind it. So please make an effort to understand all the technical details. By the way, I was very slow. Okay, so I think you are, and hopefully soon the lecture will be online. Okay? Okay, so now risking to hear from you that I am schizophrenic after having been so precise. Of course, Emilio Marchesi is not happy. He will say that I should have been more precise. But I did a degree of precision which is rather high. Okay. Now I change completely and I start talking about more vague things, apparently more vague things. Okay. So let us consider the physical object Earth. Now, it was very painful for Greeks to understand that we are not living on a flat world. By the way, 3 days ago, a stupid American built a rocket trying to prove that the Earth is flat, and he died because the rocket fell down. You know what Greeks said? That gods make crazy those they want to lose. So when Zeus hated somebody, in order to have his life lost, he made him crazy. Oh, so this man refused the abstraction which is needed for understanding the fact that the Earth is a sphere, or not exactly a sphere, but something similar to a sphere. So, let us talk a little bit. Of course, I cannot give you all the details because I would need a course in this, but let us discuss about the mathematical modeling of the place where we are living. It was a mathematical effort. So Thales discovered that when you see a ship approaching a harbor, you start seeing the top of the sail. And then you see the whole ship. So the idea is this one. I am here, the ship is here, and I see the sail before I see the ship. So one should explain to that stupid American that this is known since the 6th century before Christ. It is enough. You go and you see the sail. How can you imagine that the Earth is flat? Because the brain of human beings is, by default, considering only everything which happens in a radius of 3 kilometers. This is our ancestral tradition of being primates, like bonobos, chimpanzee. Okay? So our immediate experience, it is like virus. Virus are not existing. Vaccination. By the way, do you hear now somebody talking about the fact that vaccination is dangerous? They stopped complaining about vaccination and they want immediately vaccination. So let's go back to the Earth. Eratosthenes did manage to measure the radius of the Earth in a very precise way. What he did? He was somewhere, the sunrise rays are, they assume, you know, these are all postulates. Okay, so he started assuming that the sun is very far from the Earth, so that rays arrive all parallel to us. Okay? By the way, some Greek measured the distance between the Earth and the sun. And the order of magnitude of the distance was not wrong. Then, if you are here, there is no shadow of a stick. If you are here, you see a shadow. Right? This angle is equal to this angle. Euclidean geometry. The first one who tells you that geometry is useless, you can destroy him with this example. You stay in Alexandria. Somebody sent you a message. Of course, you need a watch and a calendar, but the watch is easy. Midday is when the sun is at the top. Okay? Then you need a calendar. Why? Because you must make your observation here the same day when you make the observation there. You measure the angle of that shadow, and you know this angle. Then you must measure the distance between here and there. A trivial proportion, and you know the diameter of the Earth, the radius of the Earth. Practical applications of this? Naval maps. You can start producing careful maps for sailing. Okay? So we knew that the Earth is more or less a sphere. By the way, in Greek books you find that because of centripetal force, it has to be a little bit not as spherical at the top. But I mean, these are details. Okay? By the way, do you know who repeated the measurement by Eratosthenes with the same precision? Lagrange. We needed to wait 2,000 years for repeating with the same precision the same experiment. Okay? Okay, now why I'm talking about this to you? We have the physical object Earth. Okay? You want to study a theory which tells you how stars are apparently moving as observed by the Earth. There are some stars which are blocked, some stars which are moving. In particular, there are some points which later have been recognized to be not stars but planets, which are making a very strange movement. So, Mercury is doing retrogradus motion. So it's doing something like that, back and forth in the sky. So we see these planets moving in a strange way. Okay? The only motion which is very reasonable is the sun. So the first theory is we stay blocked and the sun is turning around us. Very simple. However, you see other planets which are doing very strange things. So your model has some difficulties. Okay, we don't know the technical details of the Greek theory for this, because Romans were not good enough for understanding mathematics. So when they conquered Syracuse and they conquered all Greek cities, they just killed everybody. They started, Romans were like Americans, barbarians. They do not understand what they are doing, and they kidnap scientists from other countries, importing them in Rome or in the United States. Okay? Maybe Americans are a little bit more efficient than Romans. Why? Because we have printed books. So the big problem of the transmission of knowledge in the Hellenistic age and until the invention of printing, and for Turkey even later, is that you need to copy by hands books. And copying by hands a book is very expensive. By the way, you need parchment. Parchment is or papyrus, you need the support when writing. One book like that costed more than a farm. Okay? So it was very precious. Do you imagine somebody telling, write the theorems of Archimedes instead of buying a farm? Nobody's doing this. So, we do not know how they did the theory of the motion of the planets around the sun. But Marcellus, when entered in Syracuse, found a planetarium. And this planetarium has been described carefully in the Latin books. You had the sun in the center, and then planets moving with gears. So you were turning a gear, and planets were turning around the sun. And this was a possible use of this planetarium. Then what they did, this was an analog computer. They blocked the Earth. And turning the machine, they could observe the relative motion of planets with respect to the Earth. They were writing this formula for velocity and for placement for every planet. You know that Caesar, using something read in a book, managed to establish that every 4 years you need to add 1 day. And however, for every year, starting with 000, you should not have the extra day. So somebody in Alexandria could calculate with great precision the duration of 1 year compared with the duration of 1 day. Okay? So it is not possible to bet a number which is so precise. You need a theory. You need a way for calculating it. Okay. Now let's move to our modeling procedure. Do you want to study the relative motion of planets with respect to Earth and Sun? You can model every planet as a material particle. So, Earth is described with a function which gives to every time instant the position of the barycenter of the Earth. 1 point in the Earth. Okay? If you want to study the relative motion of planets with respect to Earth, if you want to calculate the duration of 1 year, so the time needed by the Earth for completing one trajectory around the Sun, your mathematical model does not need any more detail. You agree? So, if Earth has to be studied in its motion around the Sun, then the mathematical model sufficient for describing its state. So remember, for me, state is something which refers to the physical object. So the configuration describing the state is the position of the barycenter of the Earth. Okay? We are happy about this. And your theory is extremely predictive. You can say when Mercury will stop and go back. You can describe in every detail the apparent motion of the planets. Not only, you can discover new planets. In a given moment, they discovered that one planet was not moving as it was forecast to move. So, I always forget the name of the planet. Okay. Nettuno. Okay. One of the, not Plutone has been discovered later. Probably Neptune has been discovered. I don't know why I don't manage to, but we can, it is written in the. Okay. So you have one planet which is not moving in the right way. So you have two possibilities. Either the theory is wrong, or there is another planet outside whose gravitational influence is causing the observed mismatch between theory and experimental observation. Okay? I consider this is very important for a mathematical model. If you invent a mathematical model which can describe perfectly what you already know, it is good, but you can always adapt a model to describe what you already know. Okay? If your mathematical model allows you to discover a phenomenon which you have never seen before, then your model probably is very powerful. So, they have seen a planet which was not moving in the right way. They calculated the position of the eventual planet which could perturb the motion in the way in which it was perturbed, and they said, point your telescope there at this moment of the day, of this day, and you will find another planet. They placed the telescope and they found another planet. So this means that their theory was predictive. They had a theory which could be predictive. Okay? Are we happy? Is the theory of everything? Think that you want to describe the change of seasons on the Earth. You know, even if things are changing, we had winter without snow on the Gran Sasso, which is a tragedy for skiers. Okay? If you want to study how the seasons are alternating, not only you travel to Australia and you discover that when here it is summer, there it is winter. what you need? You need a model in which the Earth is not a material point. It is a rigid body which is turning around one axis and rotating around the sun. So you need the composition of day, night and day. Not only, you need that the tilt of the rotation axis with respect to the plane where the trajectory around the sun is occurring. Eratosthenes did calculate precisely this tilt, by the way. So at the end, the same physical object can be modeled with two different mathematical models depending on which kind of phenomenon you want to describe. By the way, the tilt is very useful because the amount of energy arriving from the sun depends on the relative angle of the rotation axis with respect to the plane of revolution of the Earth. So, when more energy per unit area arrives north, you have summer north. When you have the contrary, you have summer south. And this effect is dominating with respect to the distance between the Earth and the Sun. Okay? Then you are somebody who wants to bomb the walls of a city. So, what you want to do? You want to throw a projectile, a big ball, cannonball, to the walls. Okay? So you need a weapon which is capable to throw. And you need the theoretical knowledge capable to tell you which is this angle. If known this distance, you want to reach the walls. Not only. You are at the top of the walls here. And you have the possibility to fire back against the army which is arriving. You want to forecast how you must throw your balls to kill those who are attacking you. Okay? How do you model the Earth? Like a flat plane. Unless you are not throwing your balls far enough that the radius of the Earth is important in your calculations. Eratosthenes knew this peculiar distance, and he knew that for every practical applications of his age, the Earth was flat. So, you have three different models for the same physical object. You use one in some situations, another in other situations, another again in another situation. Okay, let us imagine that I want to describe the motion of the Earth in such a way that I can have a model for describing the summer, winter, spring, autumn alternate. Okay? The mathematical model for the Earth will require the kinematical description more complicated by the presence of Q, the orthogonal matrix of rotation. Do you want to study the Earth when you have an earthquake? No rigid body assumption. You will need a function key describing the placement of Earth with possible variation of distances between bacteria particles of the Earth. What I want to tell you. Many philosophers declare that mathematical modeling is useless. That mathematical modeling is not capable to capture reality. Okay? And they give as an example this. The Earth is a material point, it is a rigid body, it is a deformable body. You are crazy. The Earth is the Earth. And you are pretending to understand what the Earth is. This objection is not new, even if in the newspapers you find it nowadays. There is a Roman philosopher who is like some politicians nowadays. You know, if you study history of science and history of philosophy, you discover that everything stupid has been already said. What is very difficult to say is a clever thing. But stupid things are repeated systematically. Sextus Empiricus attacks the mathematical modeling of Greeks, telling in substance that Earth is not a material point. Earth is not a rigid point. Earth is not a deformable body. Earth is something else, and you cannot understand it. What is science? You choose the kind of phenomena you want to study. So, I want to describe the motion of planets. This model is good. I want to study the seasons. This model is good. My dear friends, earthquakes are not described so well as we hope. But it is clear that you need a theory of deformable bodies for this kind of thing. So you understand, the boundaries of knowledge are increasing. You describe more and more phenomena, changing the models. Unfortunately, theories are not increasing, occupying all knowledge. Unfortunately, it is like that. With one theory you describe something, with another theory you describe other things. You have an intersection of the two theories, but you don't have a unique theory describing everything. So, let me draw a Venn diagram for the phenomena described. Quantum mechanics describes atomic phenomena, computers, some chemical phenomena, many things. Classical mechanics describes something which happens at macro dimensions. So, for instance, you can use quantum mechanics or a clever application of continuum mechanics for electronic microscope, where you have a beam made of hundreds of atoms. Then you can use both of them in this context, but then you have a small overlap. Then you have relativity, which overlaps somehow with classical mechanics, but not completely. So, depending on what you want to study, you must choose the right model. But you know very well a priori what you can do and what you cannot do. So, the objection of Sextus Empiricus is totally wrong. You cannot have the theory of everything, but given a specific set of phenomena, you can describe carefully what happens in this specific range with a very precise mathematical theory. Okay, we have a few minutes, so I can start asking you questions which we will discuss later. How many parameters do you need for describing the position of a material point? 3. The 3 coordinates of the position. If you have a rigid body, you need 6. An orthogonal matrix is given in terms of 3 parameters. We will discuss. You can choose angles, but you know why I wanted to write you this formula? Because omega is a vector having 3 components. So the formula of velocity has 3 degrees of freedom here, 3 degrees of freedom there. So a rigid body has 6 degrees of freedom. Okay? So there are mathematical models whose space of configurations is described with a finite number of parameters. Unfortunately, these parameters are not all straight lines. So think about Q. Q is taking 3 vectors and mapping them orthonormal, and mapping them into other 3 vectors which are orthonormal, having the same origin. Okay? So think to the mobile frame vector. Okay? So zeta axis is rotated and must be in the unit sphere with center, the common origin of the two bases. Then, when zeta axis arrives somewhere, you must make another turning around the zeta axis to place the other 2 vectors. We will go in more details this next time, but the space of configuration of a rigid body is R3, Cartesian product, the sphere, 2-dimensional sphere embedded in 3-dimensional space, cross product, a circle. So the space of configuration of a rigid body is finite dimensional, but it is not R6. Okay? Do you think this is a mathematical deprivation, not essential? Think about Mercator's projection of Earth for doing maps. There is no map of the Earth which can keep distances on a flat plane. And North Pole and South Pole are not one point. In Mercator's projection, they are straight lines. So the maps of the Earth on flat surfaces are deformed, and there is no one-to-one correspondence. Why? Because a sphere is not a flat rectangle. So when you want to study the motion of a rigid body, you cannot use easy 3 coordinates for rotations. You must be more careful in what you are doing. Okay, so already for describing the space of configuration of a very simple mathematical model like a rigid body, you'll find mathematical difficulties. But the bad news, and with this bad news we end this lecture, is this one. Consider the mathematical model beam. Okay? For mathematicians here, I will tell you everything next time. A beam is a line, the mathematical model is a line which cannot be curved without spending energy. This model has been invented by Euler. We will discuss this model in all detail. Okay? But it is essential that I tell you now that for finding the shape of this beam, you need, for if S is the curvilinear abscissa in the reference configuration of this beam, you need a vector field U of S, which describes the actual shape of your beam. Okay? So the shape of your beam is a set of functions defined in the interval 0, L. You can sum two functions, you get another function. You can multiply one function times a scalar, and you get another function. So it is a vector space. And there is a button, it is not finite dimensional. So, you have models where the space of configuration is finite dimensional, and you have models where the space of configuration is infinite. And we must fight with this difficulty. Okay? So this is, I wanted to arrive here to give you the motivation of the title of the course. Okay? Okay.